a situation where you have a sphere, and let me call this sphere as a useless sphere. You will think why I'm saying useless, because you will find I'm hardly using it. What is useful here is the medium in which the light is traveling. This medium has a variable refractive index of mu, which is proportional to r, means as you go further away the refractive index will increase. As you come back towards the center, your refractive index will reduce. Basically, this sphere is not completely useless because I'll use it as origin. The center of the sphere I will use as origin for my reference points. I have to solve this problem to find that if the ray of light was initially making angle theta 0 with line passing through the center of this sphere, what will be the minimum distance the light will have? What will be the minimum distance of the trajectory of light from the surface of this sphere? Based on this information which is given, mu is proportional to r, initial angle is theta 0, and this initial is r0. Only this much information is given. A couple of concepts are going to be used for this problem. Little bit of trigonometry. Now this least distance will be when you have these two perpendicular lines, and when this is perpendicular, certainly it will pass through origin. So that is how, this is the position I am looking at, and let this be the final distance which I want, r final, and you can accordingly find this d. This d will be r final minus r. That is the only utility of sphere, that's all. So r final, that is from the, I will work from the origin, and rest of it you can easily calculate. That is not so important. So I will do whole calculation based on the origin, not from the surface of the sphere. Now let me draw a general kind of a diagram. That is the specific based on problem I've drawn. Let me draw an expanded view. If this is the trajectory and I draw x-axis, a horizontal line, this is the origin, this is y-axis. From x-axis I draw radius vector r, making an angle phi. Don't get confused with this theta 0. Theta 0, I will have a general term theta. Theta will be angle between trajectory of light and radius vector, and phi is angle between this initial reference point which I have taken, initial reference point, which is the x-axis. I take this as the x-axis. The radius vector makes an angle phi with this initial reference point at certain time. Time is variable, r is variable, phi is variable, theta is variable. So many variables are there. So it started from here. Now in small time dt, let it travel a small distance d phi. So it traveled distance d phi, means the angle traversed by this trajectory is d phi, and let this be ds. Just do little bit of trigonometry, draw perpendicular here, and it is also an arc. So this A, B and C is a triangle. If it is visible, let me draw expanded view further. That is how I am drawing a bigger view so that it is visible in camera. This is how it is. This is A, this is B, this is C. Same thing magnified. This is ds. This will be r d phi. This is r, and it became r plus dr. Though it is reducing, dr is negative here. Dr will be negative because of trajectory. R is reducing. It could have been different way also, but let me write in the same pattern. I am moving in this direction. Phi increases to d phi, r increases to dr. So basically what I am interested in is the difference between this OA minus OB, magnitude of this difference. This distance and this distance is nothing but dr. I am interested only in the magnitude. Direction is not relevant. So this is dr. Magnitude of that distance is dr. So if this is dr, this is r d phi, this is ds. ds square is equal to dr square plus r d phi whole square. and I'll just simplify dr. I take common ds square dr square 1 plus r d phi upon dr. This is whole square, and this is like this. This is one important equation which will be very useful in solving the problem. Now look here, I have another angle which I should take is the angle between the trajectory and the radius vector. I take here or I take here same point. This is the trajectory and this was the radius vector initially, which was r. So this angle is theta, this angle is theta, which was theta 0 initially. Don't get confused between phi and theta, that clarity is required. Phi is from horizontal angle from the horizontal made by radius vector, and theta is between the radius vector and the path taken by the light. So this theta is here, so tan theta is r d phi upon r d, this is perpendicular because this was the arc, so this is effectively perpendicular. So tan theta is r d phi upon dr, or I can write it as r phi dash. D phi upon dr, I write phi dash here also. Let me replace, or if I write this equation here, I don't know whether it is visible very clearly. ds is equal to square root of this, which is dr within the bracket 1 plus r square, and d phi upon dr is phi dash square 1 upon 2. This 1 upon 2 is the square root of that 1 plus r square phi dash square. And I've got the value of phi dash as phi dash is tan theta upon r. So at this is the position at t is equal to 0. At t is equal to 0, theta is theta 0 and r is r0. So phi dash at r is equal to r0 is tan theta 0 upon r0. This is phi dash, means d phi by dr, not phi. At r is equal to r0, phi is 0, but this is phi dash. Phi dash is tan theta upon r. So at r is equal to r0, phi dash value is this. Now these are some of the boundary conditions I just have written. I should have written it later, but before I forget. Now another important principle which we have to use here is the Fermat principle, and that is basically about the path followed by light. If it travels from point A to point B, it will travel straight. We want light to travel straight. Why it travels straight? Why it doesn't go like this? Because here it takes the least time. But this is possible only when the refractive index is, when the velocity is constant, or the refractive index is not varying. When the refractive index varies between 2 points A and B, depending upon the refractive index, light can go in this trajectory, in this trajectory. Depends on the refractive index, in this, depends on the refractive index. But whatever trajectory it follows an important point that it will try to reach from A to B in the least time. And the velocity here is variable, so velocity at any point of time is equal to, or if I write in this context, velocity at any radius vector r is equal to speed of light divided by the refractive index mu at that point of time. What is mu at any r? Is mu is proportional to r, so mu at any value of r can be mu k times r. So at any point, this is variable, c upon k r is the speed. I'm not saying velocity, is the speed of light at this point. It is following this trajectory, and this is the speed. Based on this variable speed, it follows a variable, a path, a trajectory, to obtain the least time from here to here. That's a different matter. Least, don't get confused between the least distance and the least time. Least distance is just a geometry. from least distance, I am only fixing a point. Least distance between two fixes a point B. So these points, least distance determines the point. Least distance from here just fixes a point in the space which is B. Initial point is already fixed in the problem which is A. These 2 points it will traverse in the least time. So what is the time taken to traverse this path with this trajectory and from A to B? The time taken is, now we can write VR is for a very short, suppose let us take a small time dt, and here let the velocity speed be v. So this is distance upon time. So my dt, value of small time elements, dt it keeps on taking, is ds upon vr. I am taking a lot of time, but there are some concepts. It is not directly relevant, but part of it may be useful in some problem. Now what is the value of VR? VR is C upon KR. So it is ds. In case I do some mistake somewhere, putting square root and all, just ignore it and correct it yourself. I am just discussing the principles and concept which have to be applied while solving this problem. Now VR value is C K R. I hope that is correct. So dt is equal to K upon C is constant. Integral R ds, and these are the boundary conditions for A to B. There are some values, depends on the function what we write. I am just writing A to B. So this is the time taken. We are using only this as far as the equation is concerned. I will not use the time taken at all to solve the problem. That's the beauty. In such problems, just write the equation for the time taken. The steps in solving such problems where you have variable refractive index is that it will take time, and that time will be of course minimum. That path it follows of course gives you the minimum time. But value of the time is not important unless it is asked in the problem. What is important is this function which you get here. That is important, not the value of dt, but I need this function, and to get this function I write this equation. Now what is the function which is coming here? dt is equal to K upon C is constant, again not relevant, and this is R times ds, and ds is that. So I get a function R times 1 plus R square phi dash square 1 upon 2 dr, and boundary conditions are A to B. These are some values from point A to point B. To get a stationary result in this equation, this function, this is a function now, should satisfy a differential equation. If you get this kind of function, what I write is, if there is a function which is in terms of say r phi dash, and there is a dr, and there is an integral, and phi dash is d phi upon dr. It can be anything. It can be t, y dash, and it can be dt. It can be any function, but you see the pattern. If you have this function inside the integral and you want result of that integral, then this function, this type of function which has variable to be integrated in terms of that variable, and there are two other variables. One is the derivative of in terms of this variable, and another is that function, that variable itself. Then it has to satisfy, it may appear difficult, it is Euler-Lagrange equation, EL equation. It has to satisfy a differential equation which is df upon d phi minus d upon dr df upon d phi dash. This has to be satisfied to get result from this, to get a value of time t. That is the only requirement. I don't need time t, but to get that I need this to be satisfied. Uh, Intuitively, once you do 2-3 times you will such problems, you will understand the beauty of such function is that moment you have a function where you have a derivative of one with respect to other, means you have phi dash, you have r, you have dr, and phi is missing. That is what helps me. Phi is missing here. See, phi is missing, and this EL equation is for this. When there are all three, this is the EL equation. But if this one is missing, means phi is missing. This becomes 0 because if in this function I don't have phi, now let me rub these parts. Let me retain the equation. This I retain. Now in this, what is the function is f is r 1 plus r square phi dash square 1 upon 2 is my function. df upon d phi is what? That is what is in such problems. You will get only such problems where the result will be coming like this. Will be 0 because phi is missing is here. That is the beauty, that is the advantage of using it, because it completely simplifies. It doesn't I am not getting the result of time. I am using this to get a differential equation. This needs to be satisfied, and once this is satisfied, I will get one interesting function. So it may appear slightly confusing. I don't know how to explain it in a much more simpler way. I repeat, I am not going to use time. To get the value of time, I am getting a function. This is a function which meets my standard form of Euler-Lagrange equation. There you have a differential equation. To solve that function in terms of integral, that condition has to be met. Even if df upon dfi is not 0, I was only saying it becomes easier for us. Even if it is not 0, still we use it. I don't know whether it is 0 or not. Now this is the function and this is the EL, this differential equation. Let me put the values in this differential equation. What is df upon d phi is 0 minus d upon dr, and what is df upon d phi dash? Df upon d phi dash is, quickly we can do it, r square twice phi dash upon 2, because this is root 2, so 1 plus, this is nothing but differentiation, phi dash square raised to power 1 upon 2. I hope this is what should come, is equal to 0. This is what I get. So this anyway was 0. Just check if the differential thing is any mistakes. Principles, just look at the principles. I'm not going into specific values. So basically I have differentiated this with respect to phi dash, df upon d phi dash, and I should get something like this. If it is correct, then I will get this. If it is not correct, I will get something like this that you can check. Now since this is 0, d upon dr of this is 0. It means this is constant. Here you have a constant, only then you will get something as, because r is there all through. It's a combination of r and phi dash. So this is a constant value. When you get such equation where this is 0, it implies df upon d phi dash is constant in terms of phi dash. So in terms of this constant in terms of r, if d upon dr of df upon d phi dash is 0, then df upon d phi dash is constant in terms of r. So I get an equation which is this. I get this is a constant. This is what I get. I get a value which is constant. This 2 gets cancelled here. So I get r cube phi dash upon 1 plus r square phi dash square raised to power 1 upon 2 is constant. That is the value. Now just put the boundary conditions. When you have reached the final value of r is r final, And what is the value of phi dash? Phi dash is tan theta upon r. At the final position, what is the value of theta? Theta is pi by 2. Here it is the angle between the radius vector and the trajectory. When theta is pi by 2 means phi dash is tending to infinity. So phi dash is infinity at the final position, or because to solve this we will use reverse. When you have such problems, just do reverse, means 1 upon phi dash is 0. Just take phi dash common here, you get r cube upon, this is phi dash I take common, it is phi dash square root, so it comes phi dash 1 upon phi dash plus r square raised to power 1 upon 2 is constant. Phi dash gets cancelled. So this is one form of equation, and I get this because 1 upon phi dash is 0, I get r cube upon r, so I get C as r final. This is r final at final position. This is the general equation, but final position is C was rf square, I think. That is what was coming. It was rf cube on the top, and underneath it was rf. So C is equal to rf square is one equation I have got. C is equal to rf square. One equation I have got. Now put the initial condition. I could have put the initial condition first. Now put the initial condition. Initial condition, r is r0 and phi dash is tan theta 0 upon r0. So r0 cube tan theta 0 upon r0, and this becomes 1 plus tan square theta 0 raised to power 1 upon 2. Just correct if there is any calculation thing. So it is r0 square tan theta 0 upon, this is secant square, secant means secant theta 0 sine upon cos, and this is cos upper, so it is C becomes, C is equal to r0 square, it should give you sine theta 0. Just in any way check that calculation part, because quite likely on board mistakes happen. So this is equal to r0 square sine square theta 0. So r final is r0 square root of, no, this is not sine square, this is only sine, it is not sine, sine theta 0. So this should be the answer. R final is